Okay, well, you got a square here. One of the corners is at 2, 2, right? The other corner's at 3, 3. So your square is right here. And you see, again, that x goes from 2 to 3, and y goes from 2 to 3. So this is actually a majority of this region here, okay? So if we get a good estimate of the volume above this square and below the curve 2 squared of z equals 2 squared of xy, then we're going to have at least a ballpark idea of how big this integral ought to be. Okay? And we could also estimate the area of this region. Okay, just start by saying, well, if it's a triangle, it's what? From 2 to 9 halves is 2.5 units, right? By 2.5. It's a triangle, 2.5 times 2.5 is 6.25. Half of that is 3 1/8. Okay? But of course, it's pretty well curved below that, so we're going to say the area is probably between 2 and 3. Okay, just simple estimates. Just to get oriented toward the geometry of the whole picture so we understand what we're talking about when I develop the integral by partitions. Okay? As I will in a minute. Okay, well there it is. The area of this is just 1, right? And if you look at the picture, it looks like the sum of these two areas isn't much more than 1. And I probably needed, I don't know, maybe I've got the curvature right. I think it curves a little deeper into this than what I drew because I didn't draw it very carefully. Okay. So, in 3 dimensions, then, we have our square, right? And we can construct a truncated parallelepiped up to the surface, can't we? Okay? So tell me what the dimensions of that parallelepiped would be. Truncate the parallelepiped above the square by the curve z equals 2 square root of xy. And give me the dimensions. And you know that you can also calculate the normal and all that other stuff, right? But mainly I want the dimensions and an estimate of the volume.